And we'll talk about the exam a little bit more next week. Okay, so if Sarav shows up, we'll stop early, but otherwise, we have some territory to cover. I started last time talking about chemical reactions and chemical equilibria, and we had this sort of simplest, using the example of the simplest possible reaction. And let me just remember quickly, just so I can remember. We had this kind of thing if T and P is constant. Then that's dg, so like the way that the Gibbs free energy changes is the composition changes, so the ends change, right? And that sort of makes sense. Chemical reactions are going to be increasing the entropy of the universe if they happen spontaneously, because that's lurking behind everything. And the way it's going to do it is by rearranging the constituents of what we have. We take some reactants and we mix them, and then we get some products. And there's still some reactants left at equilibrium. There's a maximum entropy. When that reaction happens, entropy is produced. Let's say it happens irreversibly. We don't really talk like that. We're not using that language like with gases. With compressing a gas, it's easier to think about doing it reversibly and doing it irreversibly. But the chemists, they just dump stuff in a bucket and then they run and then it may explode, right? That's irreversible. But there's an equilibrium which you could get to by taking a reversible path, I suppose, where the entropy is maximum, and by deviating from that equilibrium, you would lower the entropy of the universe, and so that wouldn't happen unless you did some work or something which would make entropy somewhere else. But anyway, the constituents are changing, so there's why would that how could that change the free energy, right? So if I break bonds and form bonds, that takes energy. So if I have a high energy bond, if I could take things that have weak bonds and rearrange them to have more stable bonds, that sounds like what chemistry does. Why does that want to happen? Well, remember, where does the liberated energy, where does the heat generated in this exothermic reaction go? Out, and that raises the entropy of the surroundings. Now I could have let's say I have a gas. Let's say A is a gas. Okay, and maybe B is a little higher in energy. But is A going to want to convert into B if B is a little higher in energy? Well, what has a lower entropy, a 50-50 mixture of A and B, or all A? Right? So the mixture, there's an entropic effect by making a mixture. So some chemical reactions produce stuff so they can mix, even if there's some heat that has to go in. This is why, when you have an endothermic dissolving of something, right, you're rearranging things. Now you might say, well, rearranging things, like if I have a reaction that I could have a molecule, one gas molecule that can break into two gas molecules. I mean, that maybe is easier to see. There's going to be more entropy with more ways of having the pieces flying around rather than attached to each other. That's a low entropy thing, breaking something, even if it takes energy to break it. So that and we'll try to keep that in mind, I hope. And as we work through it, we can point that out. But just to set the stage, the other thing we have to remember is we can't change all those ends independently, and we have these. And we talked about this already. These are the stoichiometric coefficients. That's a lot of words to say, but remember our chemical reaction. Oh, and for the A and B, nu B is +1 and nu A is -1. So the products have a positive stoichiometric coefficient, and the reactants have a negative one. And you might say, well, that's not how we do it in organic chemistry, because there's a 1 here and there's a 1 here. But remember, the way we write a reaction is to have like the sum of J, nu sub J, A sub J equals 0. And that would have 1 times B minus 1 times A equals 0 if I were to use that form here. So we have that. And this A converting to B is so simple that we'll have to also talk about a more practical one so it's clear. But let's stick with this example. So my dG is going to be mu B minus mu A dC. And remember, this C is the degree of advancement or extent of reaction. It goes by, it has several passports, right, and has several aliases, but this is the one we'll use here. And for gases, we can have our chemical potentials, and you can choose whatever standard state or reference state you want to, really. But for gases, it would be useful to just pick the same one for each gas. We have this other equation like mu. Recall, mu star. Whoops. I think I know where the eraser is by now. I use it all the time. We could say mu sub J is mu sub J star plus RT log P sub J over P sub J star. And that star would be the pure stuff. But you can convince yourself that if you pick a different thing to have in the denominator here, then it also gets sort of it compensates by showing up in the definition of that thing. And this kind of like if these indicators match, then everything always works out, because if Pj is Pj star, then I have log of 1, and that just gives me mu j is mu j star. But for a gas reaction, maybe this is the best form to use. And where we finished last time, so I'm just reviewing, as you probably noticed. We can plot g of xc as a function of xc, and that degree of reaction will adjust itself, spontaneously, until we minimize the Gibbs free energy, and we have this that idea that this is something we want to do. And in general, my dG, which was the sum of J, let me make sure my font is a good one, mu sub J dN sub J, which is going to be sum of J mu sub J nu sub J dC, because all those changes of n's are coupled by the stoichiometry. And this thing we've defined as delta reaction of G, right? Oops, we don't need to read my email. Let's see. I mean, you can if you want, but so privacy is an important thing, right? And so some people really are, paranoid about people tracking them, and shall I use Google, Gmail, or not? But see, when you're when you're a scientist, you just want people to read what you write. Please read my paper. So I don't think the CIA much cares about what I do. I'd be surprised, perhaps. I don't know. I did go to did I tell this right? I went to a conference once where there were a lot of people from Iran, and they were talking about, there was a conference about quantum computing. It was in Italy at this United Nations research place. And I get back in my office, and there's a knock at my door, and there are these two people looking pretty buff, okay, and like they were actually from Hollywood. And they go, the woman goes, "My name is Darlene Gibbons. I'm from the CIA." They wanted to talk to me about what I learned about what I learned at this conference about quantum computing being done by scientists in Iran. And I said, they don't give a poster session where they tell all their secrets. That this doesn't happen. But anyway, so they did care about that. But my email is not as interesting. Anyway, let's get back on topic here. This delta G of the reaction, just by staring at that equation, is the derivative of G with respect to C at T and P. So that's the slope. That's how, if I change C a little bit, then that's how G changes. So over here, the slope is negative, right? And so the delta G of the reaction is less than 0. Over here, the slope is positive, and the delta G of the reaction is greater than 0. And then, Goldilocks had the porridge that was just right. So there's some equilibrium C where delta reaction of G equals 0, and that's at equilibrium. That's probably is it Twitter still in your mind? Yes. Okay. That one's probably taken, don't you think? I don't know. All the good ones are taken. So if I'm over here, so I mix a cocktail of constituents which can undergo chemical reaction, and they decide what they're going to do. And if by increasing C I can lower G, then that's what I'm going to want to do. I want to lower G, and that negative slope of that negative delta G of R means I'm going to go that way spontaneously. Likewise, if I'm going to go over here, I'm going to go backwards spontaneously. And if I'm right at the sweet spot where the delta reaction G is equal to 0, then I'm happy. Now, we don't have to, like I said, we don't have to talk about the existence of molecules, but when you're doing chemistry, it does come in useful. So at equilibrium, does that mean nothing's happening? And this, this from general chemistry, and we're probably not going to get this far in this more a higher level class, but there's still A is being converted to B, and B is being converted to A, right? But if I'm to the left of equilibrium, then at the molecular level, more A is being converted to B than B is being converted to A, and so there's a net change in the amounts, right? And so A is converted on average, like averaged over all the molecules, to B. It's like a beehive. There's all these buzzing things going on, molecules converting from A to B, B to A. And if you're an individual molecule, you might not even notice the fact that you're not at equilibrium, but because you're being converted back and forth A to B. And an example of this could be like a cis-trans isomerization. Right? There are these things called double bonds the organic chemists are kind of excited about. It's kind of hard to twist them, but you could twist them if you work at it, right? So you can have like a cis and trans 1,2 dichloroethene. Did I do that right? Okay, and it could be doing this, and this one, and this one. They probably have different energies, and that was on your final last year, right? So something about whatever's going on. That could be going on, but if they're all this way, there's going to be like even if it's energetically unfavorable, which I probably isn't. let's make these big groups. They don't like to be near each other. It's going to like to be like this, right? But if they're all like this, there's some entropy going on, right? So like having some like this and some like this, it's like flipping all heads. You know, it's not going to happen. You're going to flip some heads and some tails. But if you had unfair, this is a good way to think about it. I think each molecule is like a coin, but they're not fair. You know, so it'd be you could even make a coin. People do this. Magicians will do this. There was a guy who gave talks when I was in graduate school. He was a statistician. He built a machine that would flip a dice. Always, if you put it in a certain way, it would flip it. It would always be 6 or something, or always heads. Right? You could cheat. Right? Politics illustrates this, I think, pretty. They just threw somebody out. And speaking of which, they just threw somebody out of the House of Representatives today, I think. Anyway, but so if you have an unfair coin that energetically wants to be heads, but if you flip it, it's not always going to be heads. It's going to be biased some towards heads, but you're going to get some tails in there with some distribution, right? So if they start at all heads or all tails and you start rattling them around and flipping them, that's like starting all over here, all over here, or all over here. And, you know, as the flipping goes on, the coins are going to be doing their flipping and flipping. But if you could somehow, like, what is a fraction heads and fraction tails, that mixture will evolve until it comes to equilibrium. And you're still shaking the thing. Heads and tails are still flipping back and forth. And if it's a fair coin, you're going to have 50-50 if you have enough coins, right? If you have 4 coins, sometimes there's going to be 3 heads and 1 tail, and sometimes even 4 heads. So the average will still be half and half, but the fluctuations will be big. But if I have 1,000 coins, then you'll see a very small fluctuation. In fact, if you have 10,000 coins, the average will be 5,000 plus or minus 100. That's sort of how the statistics work. Relatively small fraction, and if you have a mole of molecules, you can't tell. It looks like it just comes to equilibrium, but at the microscopic level, stuff is still going on. In stat mech, you can talk about that. That will be coming in a future quarter for you. All right, so okay, let's just make sure let's look at a real reaction. So if I have 2H, just to make sure we have our notation right. Maybe this is unnecessary, but you never know. So there's a reaction, and I have my news. H2O is a product, so it's got 2. H2 is a reactant that's got -2, and then O2 is -1. So my DG, if I work it out, you know, it's mu H2O dN H2O plus mu H2 dN H2 plus mu O2 dN O2, which is going to be this 2 mu H2O minus 2 mu H2 minus mu O2 dC. And my delta reaction is 2 mu H2O minus 2 mu H2 minus 2, oops. It always helps if you don't introduce bugs into your program. There we go. And, you know, that will change with composition, because those mu's depend on the partial pressures of the 3 gases, right? And so it'll figure out what it wants to do, and it'll come to equilibrium. All right. But, you know, let's go back to the simple one. So let's assume these guys are separately ideal gases. And like a gas of something that could undergo an isomerization or something like that. We can calculate, or we can write down an expression as promised for their chemical potentials. That's a P in terms of the standard state. And PA and PB are partial pressures. And for this problem, I'll say it once more. For this problem, PA plus PB is the total pressure. And so how does the total pressure depend on C? Does it? No. Because they're ideal gases, for one thing, okay? If they were not ideal gases, the A's may be sticking to each other and the B's may be sticking to each other, meaning they would have different. Remember back to Craig 2.0, he talked about van der Waals gases. And these A and B parameters, they would have different sets of these. Hey, how we doing? A and B parameters. Yeah, you guys lucked out. So anyway, there would be a non-ideal component. But here, if I lose an A, I produce a B, and they add up together to give me the same pressure. So the pressure doesn't depend on it. But what about this reaction while we're at it? So, like the reactants, the reactants, there's 3 moles of gas. Let's say I had one equivalent of this, okay? So initially I would have 3, and we know, actually, I know the hard way because I did this experiment in general chemistry lecture hall, and people's ears were ringing afterwards. If you mix a balloon with H2 and O2, then you provide a flame which allows the barrier. This is kinetics, we're not going to be able to talk about it, but there's a barrier to the reaction, and if the lower the barrier, the faster it will go. If I mix H2 and O2, the barrier is so high, nothing happens. But if I lower the barrier, then something does happen, and it very rapidly, exothermically, and impressively goes almost completely to products, right? So if I start with, I have 3 moles of an ideal gas, let's say, at the beginning, and if I go to products, how many moles of ideal gas do I have? Well, I take 3 molecules, and then they undergo they have their relationship, and they produce 2 molecules. So the total pressure goes down, right? And you might imagine, if there's atmospheric pressure, it's going to like that. That's going to be something that will be an advantage to it happening. But what happened? Like the entropy's lower, right? But what is the main? I mean, this is, I'm not proving this, but just you might imagine that the main driving force for this to happen is the bond strengths, right? So we rearrange this thing and we get a lot of heat. We have a delta H that's negative. And where does the heat go? Into the surroundings, and the surroundings go, yeah, man, my entropy's doing good today. And that would be the driving force. But you can see this simple reaction that we're doing here, it's not representative. I'll give you some, I keep promising, I'll give you a problem. I'll give you kind of a complicated problem that you can chew on when we get to that point. I mean, certainly by Monday. where you can you can look at all these different features at work. But this one's really simple, and I have a minute before we're going to pass these exams out. So my delta G of the reaction, which is mu B minus mu A, if I work it out, it's got this thing plus RT log PB over PA. And notice that the reference P is canceled out. Okay, so I have this thing that has just the partial pressures in it. By the way, and you'll see this when you do a problem, if you had this reaction, they wouldn't cancel out, and you'd have the partial pressures of the product squared. So for this reaction, we could write this as delta mu this thing plus RT log. Let's just write it down. PH2O squared PH2 squared PO2. But there's a problem. Can you read that? No, let me write it down here. Log, and then we'll stop. I'll rewind and talk about this, but I want to make this point here. What's wrong with that? Aside from you can't read it very well. Okay, if I take the log of something, can it have units? No, okay? So what are the units of the numerator? Atmospheres squared. What are the numerators of the denominator? Cute. So that thing as it stands has units. So what'll happen is this guy will be in there, okay? But like if we did it in terms, you'll see, if we did it in terms of mole fractions, then the mole fractions would be fine. So, and you might remember this from general chemistry. There's sometimes different. We're getting to equilibrium constants, and there's units sometimes for some of these things, or not. But this is what we get here, though. It's not an issue because that thing has canceled out. Okay, let's stop, and let's try to give you your exams back.